Section: Introduction. In this section, we will discuss how language models, LMs, typically work with discrete tokens and require a tokenizer to map text into a sequence of tokens. Most LMs today use subword tokenizers, while some use byte-level or character-level tokenizers. However, a key limitation of these models is that once they are trained with a specific tokenizer, they cannot be used with a different one. This can lead to inefficiencies when dealing with languages other than English or specialized domains like coding. Switching between tokenizers can also affect the performance of the models, making tasks like ensembling or model merging challenging if the tokenizers are not the same. To tackle these issues, previous methods focused on retraining the embedding parameters of an LM with a new tokenizer. We introduce a new concept called Zero-Shot Tokenizer Transfer, ZeTT, where we aim to create an embedding matrix for any tokenizer without prior data observation. Our approach involves training a hypernetwork on various tokenizers to predict the embedding parameters for a given tokenizer. By doing this, we can effectively detach LMs from their original tokenizer, enabling smoother transitions between different tokenizers. Our method has shown promising results in preserving model performance across different tokenizers with minimal additional training data required. By using our hypernetwork, we can achieve efficient token transfer and maintain model capabilities when switching between tokenizers. This opens up new possibilities for combining language models with different tokenization methods. For instance, we successfully substituted a tokenizer with a more efficient one while maintaining code generation accuracy. Additionally, we demonstrated the cross-lingual transfer of a multilingual model to various languages by adapting the tokenizer and reusing trained adapters, resulting in improved speed and performance. Overall, our hyper-network-based approach provides a cutting-edge solution for transferring models between tokenizers, offering a competitive baseline for zero-shot tokenizer transfer and enhancing the flexibility of language models in diverse applications. Section Summary. Introduction. Language models typically rely on tokenizers to map text into a sequence of tokens. However, once trained with a specific tokenizer, these models are limited to that tokenizer, hindering their adaptability to different languages or domains. To address this, we introduce a new concept called Zero-Shot Tokenizer Transfer, ZeTT, where we aim to detach language models from their original tokenizers and enable efficient transfer to new tokenizers without prior data observation. By training a hyper-network to predict embedding parameters for any given tokenizer, we achieve effective ZeTT, preserving model performance with only a small amount of additional training data. This approach not only closes the performance gap but also offers a competitive solution for transferring models across tokenizers, unlocking new possibilities for combining language models with different tokenizers. Section: Methodology. In this section, we aim to explain our methodology for training hypernetworks. We want to determine the parameters theta of a hypernetwork h_theta that maps input v_b, t_b, to output phi_b for a pre-trained language model. Let phi_a and psi represent the embedding and inner parameters of the language model, respectively. The loss function L of the language model depends on tokens, embedding parameters, and inner parameters, typically calculated as the cross-entropy between the model's prediction and the actual label for a given token. We do not make specific assumptions about the loss function L. The loss under the original tokenizer T_a for a text X is denoted as L, T_a, X, phi_a, psi. We train our hypernetwork to minimize the loss L_theta, T_b, X, H_theta, V_b, T_b, psi, by replacing the original embedding parameters with hypernet predictions and using a different tokenizer V_b, T_b. The flow of information is illustrated in a figure. To create distributions over texts and tokenizers, we sample texts uniformly from the training corpus. Tokenizer sampling is more complex, aiming for a diverse set of unigram LM tokenizers to encourage generalization. We introduce a method to sample unigram LM tokenizers and compute token frequencies to construct the tokenizer vocabulary. The training loop involves updating the tokenizer based on the text queue and adding noise for variance. In practice, directly minimizing L_theta from random initialization is challenging. We incorporate a warm-up stage where the hypernetwork mimics the original tokenizer's embedding parameters. This is followed by an auxiliary loss that penalizes differences between token embeddings in the new and original vocabularies. The final loss combines the main loss and the auxiliary loss with a weighting parameter alpha. The auxiliary loss is crucial for models with separate input and output embeddings. Section Summary. In this section, we develop a methodology for training a hypernetwork to find parameters that can be used to substitute the original embedding parameters in a language model. We introduce a method to sample diverse tokenizers and incorporate a warm-up stage and auxiliary loss to facilitate training the hypernetwork effectively. The auxiliary loss penalizes deviations from the warm-up stage, and when combined with the main loss, forms the final loss function for training the hypernetwork. Section: Hypernetwork Architecture. In this section, we need to define the hypernetwork architecture. We want to explain how we map the tokenizer v_b, t_b, to the embedding parameters phi_b. To do this, we represent the new tokens t_b in v_b by breaking them down using the original tokenization function t_a and embedding them with the original embeddings e_phi_a. These embeddings go through multiple transformer layers, along with a separate prediction head for the input embeddings and output embeddings phi_text in_b and phi_text out_b. The hypernetwork includes another language model that is applied individually for each token. We call this language model HLM_theta. This model learns how to combine the sequence of tokens t_a, t, into one embedding. It's important to note that we don't consider the tokenization function in this process. By using various tokenizers during training, we aim for the hypernetwork to learn to generate a single embedding suitable for different tokenization functions. We will discuss the impact of this approach later. We also test hypernetworks that do consider the tokenization function in the appendix. Regarding token decomposition, the hypernetwork takes as input the sequence of tokens t_a, t, that any token is broken down into. However, this decomposition can be complex. For example, if t_a works at the character level and the token t belongs to the vocabulary of a byte-level tokenizer t_b, then t could be any sequence of bytes, which may not be valid UTF-8. To address this, we introduce a method to convert tokenizers to the byte level by adding extra tokens to the vocabulary. This ensures that t_a can decompose any tokens. The embeddings of the extra vocabulary are initialized randomly and trained along with the hypernetwork parameters. Moving on to the experiments, we use the English subset of the MADLAD400 corpus and code from the star coder data for hypernetwork training. We maintain a 7:3 ratio of English to code data. For multilingual hypernetwork evaluation, we select a subset of 26 languages from XGLM and use data from MADLAD400. We sample languages using a multinomial distribution. For the N-shot experiments, we train on the star coder data but replace the English section of the MADLAD400 corpus with Flan v2. For evaluation, we use various benchmarks such as PIQA, HelaSwag, BoolQ, MMLU, ARC, XNLI, XCOPA, and Human EvalPack. To assess our method, we utilize Mistral 7B as the main decoder-style language model and XLMR as an encoder-style model. We also experiment with the TINYLLAMA 1.1b model. We transfer models to the GPT-2 tokenizer for natural language benchmarks and to the star coder tokenizer for code benchmarks. In multilingual evaluation, we train language-specific tokenizers with a vocabulary size of 50K using sentence piece. In hyper-network training, we train for 200K gradient update steps with a batch size of 128 tokens and a sequence length of 128. We use a Roberta-style architecture with bidirectional attention and post-layer norm transformer layers. We continue training by running hyper-network inference for a subset of tokens to keep runtime comparable. We train for 50K steps with a batch size of 32 and a sequence length of 512. Section Summary. In this section, we introduce the hyper-network architecture, which maps the tokenizer to the embedding parameters by decomposing new tokens using the original tokenization function and embedding them with the original embeddings. The hyper-network consists of a language model that learns to compose sequences of tokens into one embedding, aiming to produce a single embedding suitable for various tokenization functions. To address token decomposition challenges, we convert tokenizers to the byte level by adding extra tokens to the vocabulary, ensuring that arbitrary tokens can be decomposed. Section: Zero-Shot and N-Shot Results. In this section, we present our findings on zero-shot and N-shot results. We displayed the results for XLMR in a table. We utilized task adapters that were trained for the original XLMR model on the English XNLI dataset and swapped the tokenizer for our language-specific one. Our hyper-network was compared against various baselines such as a simple lexical baseline, FVT, OFA, and focus. We focused on focus as it performed the best among the baselines. Our hyper-network consistently outperformed all baselines, maintaining accuracy within 1% on average. It showed a 3% decrease in the worst case and a 1% improvement in the best case. Additionally, sequences were approximately 14% shorter on average for the language-specific tokenizers, resulting in over 16% faster inference. We also presented results for Mistral 7B in English and code. We observed that ZeTT posed more challenges in the decoder case, with focus performing inconsistently. Our hyper-network made significant progress in closing this performance gap but still lagged behind on some benchmarks. However, further training the hyper-network with the target tokenizer almost completely closed this gap. Notably, continued training with the original tokenizer slightly decreased performance on average, possibly due to differences in data quality used for pre-training Mistral 7B. Furthermore, we discussed the performance of the multilingual hypernetwork for Mistral 7B on XCOPA and MMLU. The hypernetwork generally improved performance over the original model while significantly reducing sequence length. Although there was still a gap compared to the original model in some cases, continued training could potentially address this gap. We then explored the application of a hyper-network trained for a base model to fine-tuned models. We found that the embedding space of fine-tuned models is compatible with that of the base model, allowing the predictions of a hyper-network trained for a base model to be used with fine-tuned models without additional training. This approach showed promising results in transferring fine-tuned models to different tokenizers. Lastly, we discussed the conversion of tokenizers to byte-level and unigram LM, highlighting the importance of these procedures in simplifying tokenizer transfer research. We also analyzed the computational overhead of the hypernetwork, showing that the relative overhead decreases with an increased number of layers in the main model.